In the previous video, we discussed the disadvantages of exact computation of the partition function and average properties of a thermodynamic system. We had to integrate those functions in the integrants with respect to large number of parameters. Therefore, as a solution, we use sampling. In sampling, the integrand is computed for selection of randomly generated states. The average of these individual computations provides an approximation of the integral. Sampling methods are often more computationally efficient than exact integration techniques, particularly when dealing with complex functions or high-dimensional spaces. Monte Carlo simulations often rely on sampling techniques to generate random data points for analysis. As the computation of the partition function z is difficult, we use Markov chain algorithm to find the average value of a property A. In this algorithm, choosing next state for system depends on the state immediately preceding it. Assume that there are two states, Si and Sj. There is a transition probability from state Si to state Sj, represented by a transition matrix Pij. The stationary probability of states Si and Sj are given by pi and pij. Based on the detailed balance condition, pi times Pij is equal to pij times Pji. Now we are going to prove that summation of pi I times Pij is equal to pij. So using detailed balance condition, the summation of pi I times Pij can be written as summation of pij times Pji based on the detailed balance condition shown here. As this summation depends only on I, we can take this pij outside the summation. Therefore, we have only Pji within the summation. And we assume that this Pji probabilities satisfy the normalization condition. That means summation of Pji is equal to 1. Therefore, we can show that summation of pi I times Pij is equal to pi j. This stationary probability is always proportional to exponential of minus beta times the energy of the energy state over the partition function. Therefore, we can write pi I is proportional to 1 over z times exponential of minus beta times epsilon I. Pi j is proportional to 1 over z times exponential of minus beta times epsilon j. Therefore, pi I over pi j ratio is equal to exponential of minus beta times epsilon I minus epsilon j. In this slide, you can see the Metropolis algorithm. In this algorithm, initially, you have to pick an initial state called x0. Then you have to set the time to 0. Then we start an iterative process where we first generate a random candidate state called x prime based on the proportional distribution pi of x prime. Then we calculate the accepting probability based on gamma is equal to minimum of 1 and the ratio we calculated before. This ratio depends on the current state and also the randomly generated state. Then you have to generate a uniform random number between 0 and 1, and then you check whether that random number is less than or equal to gamma. If gamma satisfies this condition, then we accept the new state and set xt plus 1 is equal to x prime. If the random number is greater than gamma, then we reject the new state and set xt plus 1 equal to xt. Then we set t is equal to t plus 1. The calculation of the expected value for thermodynamic property A follows this procedure. First, a sequence of comprising m configurations is generated, and for each configuration Sn, the property An is sampled. Subsequently, the thermodynamic mean is approximated through a straightforward averaging process. That is, we calculate the summation of these An values and we divide it by number of configuration.